Hello everyone, my name is Logan and welcome back to the lecture hall. For today's video we are covering section 11.3, the integral test and estimates of sums. And so we're going to start this lesson off by just looking at the series, the sum from 1 to n of 1 over n squared, and we're actually going to say, well, this is going to be the sum from 1 to infinity. And so if we look at it, we're going to see, well, this is equal to 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, blah, 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 blah. We get it. Well, if we were to put them on the graph of y equals 1 over x squared, and we were going to put each of these as if it were almost Riemann sum notation, we could kind of see, well, we get an approximation of the sum, maybe, if we had taken this series as an integral. And what we notice, or what we are interested in with series and sequences, are the convergence and divergence of said sequences and series. So, when we look here, we notice, maybe we can actually use integrals to help tell us this. And we actually can, and this is where we get the integral test for series. Our integral test states, suppose f is continuous, positive and decreasing on 1 to infinity, and let an equal to f of n. Then an is convergent if and only if the integral from 1 to infinity of f of x dx is convergent, and if the integral from 1 to infinity of f of x is divergent, then our series, the sum of an, is going to be divergent. So, what do we notice about the integral test? Well, it helps us find a way, it gives us a test for convergence or divergence, but it is limited. The integral test only works on continuous positive decreasing functions. If our function, if at all, increases at some point, and it is not a purely decreasing function, we can't use it. If it's a negative function, we cannot use it. If it is not continuous, we cannot use the integral test. But this is what the integral test is. One immediate, corollary to the theorem that we get, or from the integral test that we get, is the p-series, 1 over n to the p, is going to be convergent if p is greater than 1, and divergent if p is less than or equal to 1. So we know the sum from 1 over n is going to be divergent, and then this p-series test almost gives us, well, if it's less than or equal to 1, it's going to be divergent. So if p equaled 1/2, so we had the sum from 1 over the square root of n, that would also be divergent. This is a very important theorem to have, or maybe this isn't a theorem, but this is a very important result to have in your brain, because that will save you time on the test when it maybe tells you, hey, is this convergent or divergent? Well, if you know immediately that p-series are convergent when p is greater than or equal to 1, then you can just make your conclusion from there, rather than doing the integral test on something that looks like a p-series. We know that we denote partial sums of a series as s sub n, that is the first n terms added up, and then we know that the limit as n approaches infinity of s sub n, well, that's going to be equal to the entire sum. So then we know that if n doesn't actually equal infinity, you only choose n many terms, well, Rn, the remainder of what's left for the sum, is going to be equal to s minus s sub n. And that should make complete sense, right? We have what's left over from our true sum versus the sum we have found with the first n terms. So if we look at this graphically, well, if we did from n to infinity, well, we try to find our remainders, and our remainder of this would be equal to an plus 1 plus an plus 2 plus blah, 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 and so forth. And what is that for? Well, that's the remainder of what is going to be left over with our sum. And so we can actually bound this by the integral from n to infinity of f of x dx. Because if we look at it, we do the Riemann sum approximation, and everything is below it, so then we know our remainder is going to be less than the remainder of n is going to be less than the integral from n to infinity of f of x dx. Now, if we look at it on the other side, and we took the remainder sub n, so so all the terms after n, well, that's going to be our remainder, right? And so we look at it graphically, and if we take the integral from n plus 1 to infinity of f of x dx, well, that's going to be this line, but our r sub n is going to be an plus 1 plus an plus 2, and we look at our Riemann sums, well, this is going to be greater than. So then we actually get a bound for our remainder. We get a lower bound and an upper bound. Now we get the remainder estimate for the integral test, and it says, suppose f of x equals a to the k, where f is continuous positive decreasing function, and for x greater than or equal to n, the sum of n, or the sum of a sub n is convergent if r sub n is equal to s minus s sub n, which is the sum and the partial sum. Then we have, well, the integral from n plus 1 to infinity of f of x dx is going to be less than or equal to Rn, which is going to be less than or equal to n, the integral from n to infinity of f of x dx. And then, well, what happens if we just added an s to this, or an s sub n, and we added an s sub n and an s sub n? Well, then, well, we can rewrite some things. We know Rn is going to be equal to s minus s sub n, and well, those are going to cancel out. And then we get that the integral, or that we then get that s sub n plus the integral of n plus 1 infinity to infinity of f of x dx is going to be less than or equal to the actual sum of the series, which is going to be less than or equal to the integral from n to infinity of f of x dx plus s sub n. And so we get this handy-dandy inequality, but why the fuck does it even matter? Well, this actually gives us a better approximation to the estimate of our sum. And why is that? Well, it gives us a lower bound and an upper bound. And so then we can know, okay, well, our series sum is definitely going to be at least in between these two numbers, which then gives us a better estimate rather than just saying, oh, it's going to be less than or it's going to be greater. We have both, it's bounded, we have more information. That is all I wanted to cover for the lecture portion of the video. Let's transition to some practice problems. For our practice problems, we're going to be doing two very quick ones, and this is going to be number 3 and number 27 from our textbook. And the first one states, well, determine if this series is going to be divergent or convergent. Well, we look at this and we see, well, the sum from 1 to infinity of n to the negative 3. Well, what is n to the negative 3? Well, we know that a negative exponent, we just flip, put it on the denominator, and it becomes positive. So this is the sum of 1 over n cubed. And then we look at it, well, hey, it's a power series, or it's a p-series, right? And we're like, oh, well, it's a p-series. I paused for dramatic effect. It was probably very weird. And so we're like, well, it's a p-series, and, well, if this were p, and p is 3, well, 3 is greater than, or, well, 3 is greater than 1, so then we know, yes, it's going to be convergent. And that's all we would have to say for this question. P-series test, and 3 greater than 1, boom, convergent. Now, we move over to the sum of cosine pi n over the square root n. And it says, tell me why you cannot use the integral test. And so with this, we actually dive into the important question, well, what are the conditions for the integral test? Because we know what it works, but it has certain very limited conditions. Well, it has to be positive, decreasing, and continuous. Well, we know cosine and square root n, those are going to be continuous. But we have to think about the positive and the decreasing. Well, if we just plug in cosine pi n, that's going to rotate between 1 and negative 1. and then 1 and negative 1 and 1 and negative 1, and then we're like, okay, well, it's not always going to be a positive function. And we know cosine looks a little something like this, and so it's not always going to be decreasing. So we cannot use our integral test on the sum of cosine pi n over the square root n, because it does not meet the conditions of the integral test, those being positive and decreasing. That's all I wanted to cover in the video today. As always, there will be practice problems posted in the comment section, not the comment section, in the description of the video. And then, as always, please leave me feedback on how I can explain this better. Did I make a mistake? Who knows? And then, as always, my name was Logan. Have a great day. Thanks for watching.